Hi everyone. This lecture is the lecture 3 in the chapter 3 about digital modulation. And in this lecture 3, we will focus on the modulation with memory. There are two subjects in modulation with memory we plan to discuss in this chapter. One is linear modulation with memory, and the other is nonlinear modulation with memory. The linear modulation memory is easier, and that would be what we discussed today in these lectures, and it'll be much shorter than the nonlinear. The nonlinear modulation with memory is a bit more complicated, and for better separation of the lectures, so we cannot finish both linear and nonlinear modulation with memory, so we separate these two subjects in different lectures. So in this lecture we will just discuss about the linear modulation with memory. Okay. As we said, the nonlinear modulation takes more than 1 hour to finish. So we will have this nonlinear modulation with memory in different lectures. And today we focus on this first one, the linear modulation. The linear modulation with memory, you can find the materials in the our textbook in the practice section 3.3. The linear correlated encoding. We say a linear modulation is linear because if it satisfies the superposition principle. The superposition principle is that if we modulate on A1 and the output is B1, and if we modulate on the input A2 and the output is B2, and then if we modulate on the superposition of A1 and A2, and the output symbol would produce the B1 plus B2, then we say this modulation is linear, that satisfy the superposition principle. For example, the differential encoding is an example of linear modulation with memory. If we try to transmit signal that make a transition when a message 1 is to transmit. For example, AK represent the message, the message we are trying to send. AK is the message 1011001 and the waveform of the AKT. And the differential encoding is BK based on the message AK. And the differential encoding is that whenever there is a message of 1, then the BK makes a transition. Otherwise, there's no transition. So when AK is the message is 1, so the initial is 0 and the message is 1, then BK make a transition. And AK is 0, then no transition. And the AK is 1, so make a transition. AK is 1, make another transition. And 0, 0, 0, so there's no transition. And there's another 1, so BK make another transition. Okay, so whenever there's a 1, then the differential encoding make a transition. Okay, so that's the rule of differential encoding. So based on this differential encoding rule, can we say that this relation of AK and BK is that satisfy the superposition principle? And what is the relation? Okay, what is the relation between AK and BK? The operator between AK and linear modulator that relate the AK and BK. As we can see that BK, okay, the value of BK, K would be equal to AK exclusive with BK minus 1, right? So AK exclusive with the previous BK minus 1 that produced the BK, right? Okay, we can easily verify the relationship, right? With this operation that we have the input of AK, and whenever AK is a 1, right? Whenever it is a 1, then BK and BK minus 1 make a transition, right? Okay. Okay, now this gives the differential encoding. Okay, it's linear. The differential encoding. Is this linear modulation or not? Is this what we call the linear modulation or not? Okay, that means that does this operation, this modulation, satisfy the superposition principle or not? Okay, let's verify. Okay, let's verify whether the superposition principle can be satisfied. As we can see, the operation, if AK is the input, AK is the input symbol, and that produce BK. And then if AK prime is another input symbol, and that will produce BK prime. Then if we have the addition of AK and AK prime, and then operate with BK minus 1, right? Then we have the obviously then we can have the output is BK plus BK prime. That means that the output would satisfy the superposition principle. Therefore, this encoding or this modulation is a linear modulation. Okay. So Let's apply this differential encoding principle to the transmitter and receiver. And this is the so-called differential PSK, differential phase shift keying. This is how this differential PSK is carried out in the in a communication system. The input, again, the input is binary. That is AK is binary. Is a binary stream, and every bit is 0 or 1. And that would be the input to the encoding, right? Input to the encoding. And the output of the encoding would be BK, right? Output would be BK. And a delayed, 1-bit delayed version of BK would be the previous BK. Previous output is BK minus 1, right? So by having the exclusive of the input AK and the previous BK minus 1, that will produce BK. BK is also binary. Okay, BK is also binary, but differential encoding of the input. And so then we have this BK. Okay, BK, that is the differential encoding output. And as this BK is binary 0 and 1, so we can apply the binary PSK. Okay, do the mapping of 0 and 1 to plus or minus square root of E. Right, and that is the typical BPSK, right? Typical BPSK. And this plus minus this value would go with the basis. Okay, go with the basis, the carrier frequency, and that would make the transmit signal SK. And so altogether, that makes the transmitter of differential PSK. And as we have mentioned, this BK and AK, this is a linear modulation, right? And it also a linear modulation with memory, right? With 1-bit memory, to be precise. Why is with 1-bit memory? Because every output, right? Every output of BK is determined not just by AK, not just by current AK, the current input, but also determined by previous BK minus 1, right? The previous symbol, right? Previous symbol, right? So the actual transmission symbol, the symbol transmitted at BK would need 1-bit memory, okay, of previous symbol, previous transmit symbol. So it's a linear modulation, and is with 1 bit memory. 1 bit memory is required the current message and the previous symbol. The combination of the current message and previous symbol. So it's a linear modulation with memory. Okay. So the encoder output depends on the current input and also the previous symbol. So therefore, this is differential encoding strategy is the encoding with memory, right? It's not memoryless. It require the memory. Okay, maybe you would ask, okay, then why we need this say this kind of modulation with memory? Okay, and to answer that, okay, this is so that we can decode the message. Okay, decode the message from the difference of the phase, not on the absolute value of the phase. For BPSK, the information will be determined on the absolute phase in the signal waveform. Absolute phase, right? Because in the BPSK, in the MRA PSK, the phase of the waveform determine the information. In the differential PSK, we do not need the absolute phase, but the relative phase. Okay, the relative phase of the current symbol and the previous symbol. Okay, the relative phase that gives the message. Okay, so by comparing the relative phase, the system does not need the absolute value of the phase information. In a communication system, is sometimes it's difficult to obtain the absolute phase of a signal precisely, because of the transmission delay, because of noise, and because of fading. So the MRA PSK modulation, like MRA PSK, that requires the absolute phase could be difficult. So differential encoding offers us a type of modulation that we could just we can retrieve the information from the relative phase instead of absolute phase in the signal. That's why we have the encoding with memory. The behavior of this differential PSK can be the behavior model, or the transition from one symbol to another symbol can be described or expressed by the state diagram or the Tradies diagram. Let's discuss the state diagram first. Okay, let's define two states, S0 and S1, in the transmitter, in the signal, in the transmission signal. If the for the value of the modulation symbol BK, okay, BK is 0 or 1, that define the state, the state of the modulator, okay. And the so we have two states of the modulator, is S0 or S1, okay. And if the input the input could be 0 and could be 1, given the a state of the modulator, okay. The state, remember the state is BK, okay. And the input could be a 0 or the input could be 1. In state 0, okay, in state 0, if input is 0, then the output, okay, and then the output would be remain state 0, okay. And if the input is 1, and the state will toggle, right, make a transition whenever the input is 1 to different state of the output. Similarly, if the current state is S1, okay, the symbol is 1. And if the input AK is 0, then makes no transition. If the input is 1, then the output symbol will make a transition, right? So this state transition diagram would be could be used to describe the behavior of this DPSK. Whenever there's an input of 1, then the state will make a transition, right? Make a transition whenever there's an input of 1. Otherwise, there's no the state has no change. And we can also describe the behavior based on the Tradies diagram. A Tradies diagram is that records the state transition over the time. Okay, that's called Tradies diagram. Okay, recording the time, the transition of time of the state. So at the beginning of the time, okay, at the beginning of time, the state, okay, the state would be could be 0, S0 or S1, and if the input is a 0, then whatever input is 0, the state would remain unchanged, right? And when the input is 0, and the state would remain unchanged, okay? And when the input is 1, the state would change, would transition from S0 to S1, or from S1 to S0, right? So in every symbol time, okay, there could be 2 initial states, and every initial state could have 2 possibility of transition. No transition, or there is transition, right? So the Tradies diagram that gives all the possible Tradies, okay, of the signal transmission, of the signal transmission, and the sequence of the signal, any sequence of the message will show up on one of the paths in the Tradies diagram. Okay, would any one of the paths would represent the transmission sequence. Okay. And next we talk about the so this transition, right? This transition from one state to another state, state 0 and state 1, from when the sequence from time to time, from symbol to symbol, there is a transition. So that would be associated with the transition probability. Okay, and the okay, so let's discuss the check the transition probability. The linear modulation with memory can be characterized by the so-called the Markov chain in the probability theory. Okay, the output symbol BK. The output symbol BK can be considered as the state of Markov chain. Okay, with transition probability from the state Si to Sj. Ij would be 0 or 1. So let's have this symbol pi ij denote the transition probability, and I and j belong to 0 or 1. So pi ij, okay, pi ij, that would be used to denote probability, transition probability from Si to state Si to state Sj. From if the previous symbol is Si, okay, Si could be 0, 1, and the next state is Sj. Again, Sj is 0 or 1. Okay, so pi ij represent the transition probability from Si to Sj. Then with this, then we can have the Markov transition matrix by all the possible transitions. That is pi 0, 0. That means that the previous state is 0, and the current state, the next state is 0, from state 0 to state 0. And pi 0, 1, that means that from state 1 to state 0. And pi 0, 1 from state 0 to state 1, from state 1 to state 1, all the possible transition probability. And so if we let Pn be the vector, okay, Pn be the vector, represent the probability distribution of Bk, Bk equal to 0 or 1 at the time of Nt, at at a simple time of nt, at the time of n, and the probability of bk equal to 0 or bk equal to 1. All right, okay? The probability distribution of the value of bk at time of n. Then we can see that the probability transition from time n to time n plus 1, right? That is related by the transition probability, Markov transition matrix. Okay, the Markov transition probability transition matrix that gives the relation of this probability distribution at time n to the probability distribution at time of n plus 1, right? And that gives the product of the matrix, transition matrix, and the probability distribution, right? That gives the current and the next probability. So when we have the a sequence of probability, sequence of simple transmission, then we have then we can see the probability distribution changes over the time. So say in the beginning, right? So say in the initially we have a probability distribution P0, and then the next in the next symbol we have the probability distribution P1. Okay, and then we have probability distribution from P1 to P2 and P2 to P3 and so on, from Pn-1 to Pn. Right. So over the n bit transmission, over n bit transmission, then we have the probability distribution of Pn. And here we can see that. Okay, here you can see that by the product of all these n equations on the left hand side and on the right hand side, right? So P1 and P1 would cancel, right? And P2 and P2 and so on. So on the left, so after the iterative cancellation, successive cancellation of the product, we have Pn, right? Pn equal to pi to the order of n, right? And P0, right? Pn would be pi to the order of n and P0. Okay, so we have the relation of the initial probability distribution to the probability distribution after n symbols. Okay, the initial probability distribution could be any, right? This P0 could be like could be equal probability, not 1 over 0.5 and 0.5, could be unequal probability, like 0.2 and 0.8, or 1 over 3 and 2 over 3. Okay, 1/3 and 2/3. It could be unequal probability distribution at the beginning. and then after a few transmissions, then we can find the probability of being 0 and probability of being 1. Okay, and this is because the value, there's linear modulation with memory. Every modulation symbol would be determined by not just the current message but also the previous symbol. Okay, and so if the limiting of the transition probability exists. Now, the limited of probability transition exists, right? Then the Markov chain, we have derived previously would stabilize to a stationary state. And the probability distribution P becomes a steady state. Okay, what does this mean? Okay, this you can find this a statement in the textbook. Okay, so what does this mean? That means that in the steady state, okay, if the probability distribution P has a steady state, that means that in the steady state, the probability distribution would remain unchanged. That's what we mean by steady state. Okay, so the probability distribution does not change after in the long run, after a number of probability distribution, and that become a constant, no longer change, no longer change at all. That become a steady state. And so why is that? By the Markov chain rule, we can see that Pn, the probability distribution Pn, would be equal to the transition matrix and the product with the previous probability distribution n-1. Okay, and if there is a steady state, okay, if there is a steady state, that means this Pn equal to Pn-1, that equal to P, right? Then this steady state, then we have this P into this steady condition. Then we have P equal to pi times P, right? Now that means there is a steady state. Then we can see that what is this steady state? What does this steady state means? This steady state is actually and the eigenvector, right? P is the eigenvector of this matrix pi, right? P is the eigenvector. The vector P is the eigenvector of this matrix pi with eigenvalue of 1. See? Right? So if the steady state, okay, the steady state exists, and that steady state would actually be the eigenvector of the Markov transition matrix, right? The eigenvector would represent the steady state, okay? And let's try to give an example, okay, to explain this Markov stabilization and stationary state. For example, if the source, okay, the binary source, has a random probability, random initial probability is p and 1 minus p for 0 and 1. P and 1 minus p for 0 and 1. P is the any value between 0 and 1. That is the probability of being 0. And 1 minus p is the probability of being 1. Okay? And then assume that all the transition probability is 1 over 2. Okay? That means that this is the transition probability. The transition Markov transition matrix, right? And so all the any transition is 1 over 2. It's probability 1 over 2. Then we can easily verify that the product of this transition matrix would always remain the same. The product of this transition probability would be all the same, is remain 1 over 2 all the time. In this channel, okay, the transition probability would actually depends on the channel and the system. Okay, if say we have a system that has this transition probability, then we can see that the limit of the probability distribution at time n, that would be equal to the p0 and with n times of transition, right? P0 and n times of transition, that gives Pn, right? That's what we have, right? And this the limit of the transition of pi to the n would be is all 1 over 2, right? And the initial probability is any equal or unequal probability of p and 1 minus p, and the product okay, after the transition, you'll be always equal to 1 over 2 and 1 over 2, equal probability distribution at the output, right? And then the probability distribution Pn that enters steady state, right? That gives then we have a steady state of the transition of the probability distribution that would remain unchanged. Okay, so we have given the example of the linear modulation with memory. Okay, and a typical example that commonly used for communication is the differential PSK. Okay, differential PSK, that is 1-bit memory and is linear modulation. Okay, and so that the message is encoded in the relative phase. Okay, relative phase of this symbol and the previous symbol. Okay, so that's okay. So that is for this lecture about linear modulation with memory. Okay, thank you, and see you for the next lecture on nonlinear modulation with memory. Bye bye. Thank you.